Hi, everyone. I just want to go over what we did was it yesterday now, gain margins and phase margins. So let's talk about that. Gain margins and phase margins. Okay. So let me motivate this a bit first. So let's say you had a fairly primitive heating system in your house, and there was no thermostat, and you had to attend to the knob that controlled the temperature all the time because you could never get it quite right. Basically, you were the feedback mechanism that was setting the temperature. Okay, so let's say that the furnace, we'll designate the furnace with this block, and we'll assume that the furnace had a transfer function of G of S, and then the output, which is the temperature, basically was that. And here was you, okay, trying desperately to change the temperature to make sure it was okay, and you never got it quite right. So you decided to put in a negative feedback. You decided to get a thermostat, and so you ended up, and that would control the temperature for you. So you ended up with this instead then. So, oops, so you still have the furnace, right? And it still outputs the temperature, okay? But now part of that temperature goes back through a feedback block, okay, which I'll call F feedback, okay? Then up to the summer, all right, plus minus. And what's coming in now is whatever your set point is, whatever the temperature you want, okay? Now, the kind of question you would ask here in doing this, in adding this feedback loop is, I mean, have I caused the system to become unstable? So possible scenarios, okay? So when, let's say you change the set point, say you increase the temperature, you get something like that, right? So that's the temperature change over time. That's the temp, right? You get that, which is, that's what you'd like. Or is the thing unstable? You get different colors. The thing unstable, and instead you get something that looks like that. Okay, and that's possible, okay, with the negative feedback. And as we've learned, if the phase shift of it is enough and the amplification back on the feedback is sufficient, this could break out into oscillations. And you certainly don't want that in your when you're controlling the temperature of your house, right? 1 minute is high, next minute it's low. So this is an example where you don't want oscillations or instability. So the question is, how can you figure out whether adding this feedback loop, right, is going to cause the system to be unstable or not? Now, the way to do this is, I mean, there are different ways to do this. I mean, you can ask two questions, I guess. Let me write down the two questions here. So question one, first of all, is the new system stable or not? Okay, that's probably the first thing you want to ask, okay? And the second question you want to ask, if it is stable, how close are we to instability? Now we ask that because although, when you looked at this system, it turned out to be stable, maybe it's on the edge of stability and instability. And due to component variation, that might push it into the unstable region, okay? Because your knowledge of G of S and F of S won't be perfect, okay? And you really want enough of a margin so that to be on the safe side, so that you get this, okay, and not this. And that's what the gain margins and phase margins are for. For either of them will do. But it sometimes depends on the application. Sometimes it's better to look at the phase margin, sometimes the gain margin, but they'll both say the same thing, right, in the end. And the margin basically will tell you, how close you are to instability, right, or how close you are to stability if you're already unstable. So that's what we're going to find out. So the first question is actually quite easy to answer. We know how to do that, right? How to figure out whether this thing is stable or not. The way we do that is we have to work out the transfer function for this system, okay? Now, you probably remember from maybe the first week or second week, it's fairly easy to turn this into a relationship between the input and the output. and that was as follows. It was the output was the set point Q of S, right? That's our input, times G of S over 1 plus F of S times G of S, okay? Remember, we probably did it in terms of Y out equals Y in, was it A over 1 plus AK, okay? We did it like that. So to work out this, whether the system is stable or not, given your current knowledge, what you would do, of course, is you'd pull this. This is the characteristic equation. So this piece here, I should point, this piece here then is the transfer function, okay? Because that's the input, right? So that's the transfer function. What we would do is we'd pull out the denominator, all right? We'd pull out the denominator and then set it to 0 and then try and find the poles, okay? Find poles. And if the poles are negative on the left-hand side of the plane, we're happy, okay? All right, now that doesn't guarantee it'll be stable because, as I said, we could be close to the edge of stability and instability, and based on the manufacturing tolerances of the devices we had, it may tip it into instability. All right, but at least if we find that it's stable, we're on the good side anyway. To find out how far we are from potential instability, we need to work out the gain margins. Okay, so that's what we're going to do next. So let me first draw some. So question 1, you'd answer it just by working out the poles. Okay. Question 2, so that should be answer 1, and this will be answer 2. Right. So for answer 2, if stable, how close? Sorry, how close are we to instability? Right. We have to estimate the gain margin and or the phase margin. All right, so let's describe this as follows then. So I'm going to draw. So the first thing you have to do is write out the Bode plots, and you put one on top of the other, right? So usually you put the amplitude phase plot over the phase plot. So this is the phase plot here. Okay, that's the phase plot for the Bode plot, and this is the amplitude plot. Okay. The axes, the x-axis is the same on each. It's always the log of the frequency. And this one is usually, for the amplitude, is usually decibels, which means it's logged. That's an important point. And then this one here is just usually degrees, not radians, interestingly degrees. Okay. All right, so I'm going to sketch some plots here. So this is might be your typical amplitude plot. And then here, then, so we have a different color. This might be your typical phase plot. Okay. There are two important points on both these y-axes. The first one is the 0 point on the y-axis. Now remember, log of 1 equals 0. So this represents unit gain, okay, effectively, all right, unit gain. So there's that line, and now what I'll do is I'll extend that line across, okay. The other important one is the place where the phase crosses the 180-degree line, okay, and I'll extend that across as well. All right, and you remember that if the line does cross the minus 180-degree line, then there's the potential for instability, so long as at this point the gain in the amplitude plot is amplifying. And so just remember that anything above here is amplifying. Anything down here is attenuating. Okay. All right. So if we amplify and we're at minus 180 degrees, that's bad news. Okay. All right. So there's a couple of points we have to note. So this crossing point, let's see, this crossing point here, this one here, I'm going to call it omega p. That's not a very good omega. Try again. Omega p. Okay. And this crossing point here, I'm going to call omega g. Okay. All right. And I'll word these. So omega g is called the what's it called? The I can't remember now. The gain crossing frequency. Okay. It's basically where the Bode plot passes the 0 point. It's the frequency where it crosses the 0 one. And then WP, that's just the other one. That's the phase crossing point. Okay. All right. Now I'll do this more formally in a minute, but what you essentially do is you draw two lines, one line extending from WP all the way up through the two graphs, and another line extending from WG all the way down to the amplitude one. Oops, we do that again. Okay, all the way down to here. So we end up with two. That's not good either. Let's try again. Okay, here we go. That's better. Okay. All right. So we got two lines. Okay. Now you'll notice that so this system, you probably should spot that this system is actually unstable. And the reason it's unstable is at the 180-degree line, a point, right? You notice that we're above, the blue line intersects above 0, and so that means it's amplifying. So not only do we have a minus 180-degree shift, but we're also amplifying, and that's bad news. So it's unstable. Okay. So we really want to compute, and this is the gain margin, this bit here. Okay, that's the gain margin. All right. If we take the other line, we start here and go down until we intersect here, this distance, right, is the phase margin. Okay. And that should be below in order for it to, if that's below, that's also unstable. All right. Okay. So let's one of the confusions I think I find in this bit of the area, and I think we saw that yesterday, is the signs. All right. So I'll give you a formula to help you do that. So if the gain margin is above the green line, then oddly enough, this is negative. So the gain margin is negative. If it were below the green line, it's positive. Okay. Now for the phase margin, if it's below the line, it's negative. Okay. All right. Let's go through the formal procedure for computing these. Okay. So let's start there. So let's start that. So the procedure, and that'll become clear when we do the procedure. Okay. So first of all, the gain margin. Okay. So how do we compute the gauge margin? First of all, number one, find omega p. All right. Omega p is this bit here. Okay. It's this bit here. Right. That's the phase crossover point. And that's where the phase plot for the phase plot line intersects the minus 180 line. So find WP, okay? Otherwise known as the phase. I guess I should keep the same color. Otherwise known as the phase crossover point. Okay. And I called it the phase crossing point. Okay, but I'll call it here the phase crossover point. Okay, so this is where the Bode line crosses, the phase Bode line crosses minus 180 degrees. Okay, that's the magic number. Okay, so number two, extend a line from this point, IWP, into the amplitude plot, amplitude plot. Okay, and so this is what I did here. So that's the WP, and I took a line that went all the way up to there. I crossed over these two lines. All right. Okay. Number three, and this is where you actually get to compute the gain margin. Measure the distance 0 minus the intersection point. This is an odd one, the intersection point on the amplitude plot. If you do it this way, you'll get the right sign. So, for example, it says 0 minus the intersection point. Okay, so we got 0. The intersection point is here. Okay, and note that's higher than 0. All right, so a number minus a higher number. So let's say this was, say for example, this was 10 dB. Okay, all right, so that means 0 minus 10 dB. That of course equals minus 10. Hence, the gain margin is negative. All right. Okay. Now, what the books also refer to this as, and this is why then it's sort of the signs make sense, I guess. They also refer to this also referred to how much the gain, right, on the upper plot should be increased. Okay, increased to raise the magnitude to 0. Right? Oops, not theta, 0. And of course, in order to quote unquote raise this number to here, we have to subtract. Okay, all right, and hence it's negative. All right. So that's the gain margin. I guess one thing. Well, I guess we should finish this off. So if the gain margin is positive, well, let's say negative, because we had a negative on the diagram, is negative, then the system is unstable. Okay, so your thermostat is going crazy here at the moment, right? And what you need to do to fix it, you need to try to drop this. Basically, what you can do is you can try and pull the Bode plot in this direction. If you pull it in this direction, eventually, well, actually what happens is this distance gets smaller and smaller and smaller until eventually it disappears and then goes underneath the green line, right? So you'd have to reduce basically the bandwidth, right? The bandwidth. There's one thing I should have said, which I forgot to say on Tuesday as well. This is actually really critical. I don't know why I kept forgetting it. These Bode plots that you see here have to be done not on the whole system, but on the loop gain. Remember, we talked about this term here, FG or AK. That's the loop gain. That's the critical piece, right? It's what's happening to that. It's how much phase shift you get in that portion, which is basically this bit, right? So the loop gain is basically this bit, that bit, right? So how much phase shift you get in that, and how much amplification you get in that, right? Or how much amplitude change you get in that. So that's really important, right? It's the loop gain. Can't overemphasize that too much. It's the loop gain, the loop gain, the loop gain, not the whole system, all right? Not the whole system, the loop gain. I should have emphasized that at the beginning. So it's this piece here, okay? That's what we've got to look at. So these Bode plots are of this component, not the whole thing. All right. One other thing is, so these are margins, okay? So these are margins of safety, and this applies to electronic circuits or whatever you have, motors that are controlled by PID controllers, etc. The margin they will indicate is you should be 20 dB away from the 0 line, right? So what that means is I really want to be here somewhere, okay? 20 away. Of course, I don't have a chance in this case because I'm negative anyway. But if I wanted to stabilize this particular system, I'd have to reduce the bandwidth of this blue line, such that I end up with 20 dB. The phase margin goes positive, and I have 20 dB. Right, that's the sort of recommended rule of thumb, to stabilize an unstable one. What about the phase margin? Yeah, so very similar. Right, but with the phase margin, so the gain margin, you were dealing with decibels. The phase margin, unsurprisingly, you're going to be dealing with degrees. Okay, all right. So what do we do? Okay, number one, first of all, we find omega g, and that is the gain crossover frequency. Okay, oops, this is where the Bode line crosses 0 dB. So that's the basically the amplitude Bode line. So what we're referring to, of course, is this, where is it? This bit here. Okay. So where the blue line intersects the green 0 line, I need to mark that. Okay. Then, just like before, we'll extend our line, right? We'll extend a line, this line here, all the way down. Okay. So it cuts right across all the curves. So let's write that down. Number two, to extend line. Okay. I'll just say extend line, right? Or I can say extend line into the phase plot. Okay, number three, now this is where you actually measure it. Measure the distance from the intersection point. I'll show that in a minute. Intersection point and the minus 180 degree line. Okay. So the intersection point is this, right, where the red line intersects the purple line. And I need to measure this distance here. Okay, I need to measure this distance here, right? Distance is there. And that's my phase margin, all right? And the formula to compute this is phase margin. I'll just write it down like this, is the intersection point minus 180. So it's basically adding 180, okay? Right. So to give you an example, let's say this point here, right, where it intersects, let's say it was minus 190 degrees, okay? So the phase margin then is 0 minus 100, no, what did I do? Sorry, it's the intersection. What did I do? Intersection point. Yes, so it's wrong way around. Sorry, hold on. So it's 190 minus 190, and then it's minus 180 minus, again, it's just adding up 80, basically adding 80. So that gives us minus 10, yeah, minus 10 degrees, okay? So it's negative, hence negative here, okay? Right, it's negative, right? Right, so it's the intersection point, this number here, minus 180. Okay, and that's when I get my phase margin. And then finally, just to finish off here, if PM is positive, the system is unstable. Oops, sorry, stable. Okay, so in this case, it was negative. right? Negative. That makes it unstable, which matches the fact that this was negative up here. Okay, and that definitely told us it was unstable. So they will match each other. Okay, they won't give you opposite answers. So they're both claiming that this system, this particular one I drew, was unstable. All right. And then, like the gain margin, there's also a margin, and the margin, a good phase margin should be, should be 45 to 60 degrees from the minus 180 crossover point. Okay. All right. So that's it. Maybe you can do one. Let's do one more example, right? Just for the hell of it. So let's draw show a random Bode plot and see what we get. See if we end up with a stable or unstable one. So this is going to be decibels. This is going to be degrees. That's log omega. That's log omega. All right. Omega is the frequency. Let's draw one. Shall we see what we get? That one, and then I'll do different wrong color. Let's do a different color like that. Okay, let's see what we get. So first of all, I'm going to mark the 0 point, put a line across there. It's that one, and then mark the 180 degree one, minus 180 degree. This goes there, let's say. Okay, so I got those 2 points. All right. And those are the WG, and WP. Okay. Next thing to do is to extend lines. Okay, so I extend a line. Yeah, well, this is clearly unstable. And then I extend another line from here. Yeah. So what I do is I find this point here, right? On this point. Well, this point is 0. Okay. And then what does it say? It says it's the intersection. Where are we? Intersection 0 minus intersection point. Okay, so 0 minus intersection point. So let's say the intersection point was 30 dB. Okay, so 0 minus the intersection point is minus 30 dB. Definitely unstable. All right, definitely unstable. The phase margin. What was this? This was the intersection point minus 180. So let's say, just for sake of argument, it was minus 280, because it'll make the arithmetic easy. And then it was 280 minus 180, which equals minus 100. Okay. So again, that's bad, right? So that's negative as well. And so that's how you do it, right? I wonder if I could do an example where I get the opposite one. Let me see. Yeah, no, I think that'll do. All right, so that's that. I'll post this now. Okay. All right, thanks.